part about how to think about approaching problems to do with data, and sort of what are kind of various hidden implications behind it that we might not have fully reflect on in our everyday to-day work. So as this talk progressed, it's now more and more about this. So if you're hoping to see a lot of screens full of Clojure code, you're going to be slightly disappointed. But seeing as, at least going by the other talks, I'm a bit of a black sheep here because I think I'm talking about the only functional language that's actually dynamic and so forth. Probably you're not as interested in the minute details of Clojure, but rather just what does Clojure, or maybe even any functional programming language, brings to the table in terms of working with data. Now, our story starts in this, with this unfortunate division where many people see data science as being kind of fundamentally different from programming, or they have this strong division where you, on one hand you have people who identify themselves as data scientists and they think of themselves as primarily as mathematicians, statisticians, and so forth, and on the other hand you have programmers who just want to program or something. And this kind of, I think that if you look at a lot of tooling, it just reinforces this division, but this division is utterly baffling to me, because I think it's just one continuum. Fundamentally, what most of in doing data science is about thinking how to represent data. So it's about encoding and representing data. And this is exactly the same thing we're doing when we're programming anything else. It's just a question of doing various transformations. So it doesn't really make sense to think about these two strongly distinct things. Now, I then dug a bit deeper into this and thought about it longer, and of course this is not something that I came up with, but it's rather an observation that's pretty old. Now, for instance, Richard Gabriel, a Lisp programmer, identifies this kind of two paradigms as on the one hand having a language paradigm, and on the other hand having a system paradigm. And the idea is that with the language paradigm, you do most of your thinking up front, or rather you're working within an axiomatic system set up by the language. So it's a question of just manipulating various symbols and rewriting them. And this is like the more mathematical way. While there's the other approach, which is kind of more natural to or more common to the Lisp tradition, is this system paradigm, where you are building a live system, and the development process is essentially a dialogue with the system where you kind of slowly build it up, and you don't really know the rules under which you're operating as you start, but rather you build them along to help you go along the way. And I think this division is also what's behind, is rather than manifested in things like this division between data science and engineering and so forth. So it's fundamentally a question of how we approach problems and how we try to solve problems. Now, I think a lot of this, even though it might sound that that one approach is better than the other, I'm very certain this is not the case. I think that fundamentally what this is about finding a model of thinking and approaching problems that best meshes with the way you think. Like for me, I found the best match so far in Lisp, especially in Clojure, but that does not necessarily mean it's like the right way to do it. However, there are certain instances, especially when doing the more of exploratory work with data, where it does make sense to kind of not be limited by having some very strict rules up front. But like a lot of things that I'm going to talk about, I think can be applied to both ways of thinking, just a question of how we rearrange the bits and approach the problem as such. Right, so now, fundamentally, if going back to this kind of division, and where I think that a lot of current tooling available for data science goes wrong, is the main building block, this notion of a data frame. Like, how many of you know what a data frame is, like in a Python context or R or something? Okay, so basically the idea is that you have this kind of sort of a cross between a table and a matrix, which is your primary representation of data. And that's like, it's problematic because it conflates two different things. It conflates a concrete representation of data, because it's like you have this fundamentally a columnar storage, which is convenient for all of the operations you want to do on this, but this is kind of an implementation detail, and it conflates this with representation in terms of the data structure you're using. And this has all sorts of problems down the line, because then you very quickly come to operations which just can't be naturally expressed within this mold of having a 2D table. And this is where then tools like pandas in Python, similar, start to break down, and some things become either needlessly hard and verbose to do, or very slow. Now, Clojure, on the other hand, what it's really, and most Lisps, if they excel at anything, they excel at just manipulating data structures, manipulating and encoding, re-encoding them. So, what I propose, and like, in my works I've proven that is maybe a better way is to start with just having some very simple building blocks and just continue with this Clojure's notion of manipulating structure rather than trying to find this abstraction for mathematical data as if it were so different. Especially since, like, when you're working with real world data, what happens is that you have it tends to be very heterogeneous and probably messy. So you just mapping it to something as pure as this concept of a matrix in mathematics just doesn't make sense. And if you look at like the time spent doing data science, what basically happens is that unfortunately you spend the majority of time in the most unglorious part, which is just preparing, cleaning data, and getting to a shape where you can actually use it. And then the next thing is you just apply various models or libraries that somebody else written, and the least time is actually spent on the most glorious part, where you're developing a new model or just implementing something from an article. But if you look at the state of libraries and toolings, now most actually optimize or focus on the latter two, meaning that they assume that the data is already in a shape that you can more or less use, and then it's just about having all the various libraries and models available which you can use. But this is the part where you're actually spending the most time, and this is the least well served. So the majority of my talk is just focus on how to think about this. So again, going to just working with data as such, rather than in a more of a programming or transformative sense, rather than thinking about various mathematical models to build on top of that. Because that turns out to be relatively easy in the sense of how long it takes, and also if you look at the classes of problems you might have, it usually, like, unfortunately, a lot of times the harder problems are just you have some mess in the data you don't know, or there's something wrong in your entire ETL system, and you have to figure that out rather than trying to figure out why some model doesn't work. So to put it in another way, and this is again a drawing from tradition of various dynamic languages, in this case Perlis, Larry Wall, easy things should be easy and hard things should be possible. And this, I think, like, this very easy things should be easy oftentimes break down in a lot of the approaches to doing data science because of those kind of false divisions. So, and why is this kind of why it's so important to have kind of for easy things to be easy? It's because probably doing data science is one of those unique cases where actually speed of answer, how fast you solve a problem, is very important. Now, usually in programming, it doesn't really matter that much if it takes me 2 hours or 4 hours or something. But when you're doing data science, and if you look at this in the context of your whole organization, and trying to, especially if you want to have a data-driven organization, the thing is the speed of answers matters. It's like, based on my experience, there are like roughly 4 different classes of how long it takes to arrive at an answer. Now, first of all, in the ideal situation is if you can arrive at an answer in 2 minutes or less. This means that as you are in a meeting, as there's a brainstorming, and somebody has a question which can be answered with data, you can pull this data out immediately and actually inject it into the conversation as it's going on. This is the most powerful thing. This is like this ideal of what it means to be data-driven for me. But of course, to do that, you have to have powerful enough tools that simple things can really be simple, and you can just immediately check something even though you've never thought about doing this before, so it's not already somewhere stored, it's not prepared. You actually have to do some computation, some calculation to arrive at the answer, but if you can do it like in 2 minutes or less, this is the ideal. Then the next are tasks that take about, let's say, 20 minutes, half an hour. It doesn't build, like, the exact divisions here obviously don't matter, but the point is that kind of small tasks that you can squeeze within your day and still do them without really budgeting a lot of time to do them. Now again, the thing is that the problem, if it takes longer and it's something that you probably need to budget for and put on a in a sprint or something, it's going to take a week, maybe 2 weeks to arrive at an answer. And what then often happens is that the question isn't even relevant anymore. Like the decision has been made or the question has been reformatted, something like that. And this, what just happens is that, first of all, you aren't delivering as much value as you can, and also just your organization as a whole doesn't move as much into the data-driven direction. Rather, the other stakeholders can't depend on getting the answers quick enough, so they stay in their old ways of making decisions rather than fully embracing having data. So that's why it's so important. Now, obviously, in all cases, you also have like big projects which take months to do, and here it's not. Once you're at this stage, it doesn't really matter, like the speed of answer doesn't matter as much, but this is, again, getting more into the purely engineering part where you need to build a large system or something. So, now, with a lot of those things in mind, I released a library for working with data in Clojure. Now, I'm not going to go all that in depth to it. I just kind of want to emphasize some of the design decisions behind them, or comment on those design decisions. Now, the first thing is that it doesn't use any specific data structures, rather just builds on top of the existing Clojure abstractions and provides new functions to work on them. Why is this? Because this means that you first of all, you don't have to have this complete buy-in, but you can just use a couple of functions, and it works nicely with the rest of Clojure ecosystem. It kind of also echoes what Eric was talking about previously, that the more kind of you develop a complete new language or subset of language, the more problems you have with interfacing with the rest of the world. So kind of try to keep this minimal. The second thing is, I very much like that the things are composable in terms of you can just kind of piece bits and pieces together and just kind of, or build very simple pipelines of transformations, and just one thing can flow into another. Now, this has some concrete consequences. One of them is that even when designing domain-specific languages, I still tend to not use macros. Now, I know that Lisp, one of the kind of main selling points, or at least what makes Lisp famous, are probably its macro system and its culture of using macros to build small languages on top of Lisp and kind of extend it with that. And that's all very well and fine, but once you have a powerful enough language, which most Lisps are, especially like Clojure definitely is, what happens is that if you really think about it, there aren't that many instances where you actually need macros. There are some, and they're immensely useful and powerful, but many things can be done with very little loss of brevity by just kind of using functions, and especially embracing this kind of Lisp paradigm of code being data. So just kind of you encode some of the computation in data structures, and then just you evaluate those data structures and use that to kind of guide the execution. The next thing is kind of this do what I mean. This is something, the notion of this I lifted from Emacs, but the idea is that, and this is like probably the part where we're actually doing exploratory data analysis differs mostly from doing some proper engineering work, because like you have a lot of principles in what it means to write solid code from the engineering standpoint of view. Like you don't want to repeat yourself, and you want to be kind of explicit and things like that. But while doing exploratory code analysis, exploratory analysis, you oftentimes you want to sacrifice some of those principles, because it just adds friction and in terms of how small of a chunks of code we're looking at, and that most of this code might be just kind of run once and essentially throw away. It doesn't make sense to make the same compromises. So like, do what I mean means that kind of the library tries to be smart and guess what's actually what you want to do. So maybe at some points it's just going to auto-sort it for you. It's going to be very liberal with the inputs you can put in, and just do various casts and transformations for you and things like that. Now, these are things that in writing a library or some other production code I would necessarily do, but here they make a lot of sense because they just remove the most usual points of boilerplate. And then the last thing is, as I said, because we fundamentally want to kind of think or rewrite our problems as doing structure manipulation and encoding, what you also needed is strong support to work with vastly nested data structures. And here, this notion of what it means to have a nested data structure can be quite general in the sense that, like, in Clojure, most data structures are actually also going to act as functions. So basically, if you have like a map, it's also it acts as a function over each keys. So if you put in a key, so if you call the map with key as the argument, you get the value which corresponds with this key out. And so it means that there is like this huge difference between reaching out into a structure. And, oh, by the way, the same thing applies to vectors and so forth. So there isn't much difference in reaching into a structure than calling a function. So here, nested can also mean there's some combination of calling functions on your data. So you basically first maybe reach into the function, then so you get reach into a data structure, so you get some smaller data structure out. Then call a function on that, which gives you another different data structure, and then call another function on that. And all this can just be basically thought of as actually the structure in itself. And so the path you take doesn't necessarily mean needs to be some parts of the data structure, but just transformations that you do, and it's like the whole path of your the whole path that you want to work with. And this library kind of allows you to do that in a relatively straightforward and natural way. Right. So now, why this compromise with trying to focus on having things compose nicely? Because I think this is like the key to quickly iterating, that you just kind of want to have this various small replaceable bits and pieces that you can tie together and build bigger system out of it. And especially like when trying different things and not being sure where you want to go, I think that just having various patterns you can apply is very important, replacing things and stuff like that. So that's why it kind of turns out that this is gives you a lot of leverage in terms of how well you can work with your data. And this is like a quote that I just love. Like, on one hand, it says, composition is about decomposing. On one hand, it seems like an awfully banal thing to say, but it's also has this profound implication, especially if you look at it from the perspective of how actually Clojure as a language is built. This is exactly, it's built on top of this realization. Now, if just a small historical note, which is going to be probably half wrong, but anyway, like Clojure effectively started as a project to just have Common Lisp running on the JVM and .NET, and then slowly Rich Hickey, the author of Clojure, kind of realized that he can do things better, and then drawing from his experience working in Common Lisp, you then now have Clojure, which is essentially Rich thinking about how he was using Common Lisp, the things he liked, things he didn't like, things that repeated, and then trying to build a language with those realizations in mind. And like what makes Clojure powerful and this kind of like sweet spot, for instance, for me, and turns out a lot of other people, is that the small bits and pieces, how they tie together, are very well thought of. And so, so you have this ability to reuse the same thing over and over again in different contexts, and the things just work and tie together. And it's exactly because this approach of first decomposing what's actually going on and finding the primitives that are really behind it, and then using those primitives as the main building blocks, and then maybe build something else on top of it, but still having those primitives available to recombine them in various ways. It's basically a reformulation of the Perlis idea that it's better to have 100 functions operating on one data structure rather than 10 data structures with 10 functions for each one, because it just gives you greater uniformity and greater expressiveness. And also it's just easier in terms of developing, because you are essentially coding against the same API in most cases, rather than thinking, oh, does this work in this case or not, or something like that. Like those of you who, for instance, worked in Python with pandas know, like the moment you start to work with groups, some things that work on data frames work and some don't, and so things like that. So just abstractions just break. Rather in Clojure, you have this kind of very unified way, and as long as you have a collection, which is you know that like how things are going to work, and you can use any function that is either in the core or anyone written to work with collections, and just kind of put them all together. This is also where this idea of the minimal buy-in ties in, because I just want this to be freely, to be able to combine it freely with other libraries in both directions. And the other thing with composability, which is maybe kind of specific to Clojure Lisp or Lisps, this I noticed it here most, is that just like this, how the code looks visually. In Lisp, as you write enough Lisp, you'll notice that the code tends to have this kind of very distinctive patterns, where you even, if I would blur out the various tokens, you would still kind of get the this rough gist of what's going on, just based on how the code looks visually. And this is something that I like a lot. It's something that's very helpful to me. Now, it's in a lot of ways maybe just kind of a aesthetic thing, not as important, but I think this kind of aids understanding on a maybe sort of not exactly a level of meaning, but rather just kind of how it primes your thinking and what kind of associations it triggers. So that's again another argument that you want to have kind of composability which promotes the same structuring of code as you would have in normal Clojure program, rather than having some completely different logic behind the DSL you wrote. Right, so now this being like Lisp, one of the big selling points is obviously this kind of very live programming environment, and especially when doing exploratory data analysis, this can be a great aid. Now, but it also has kind of some problems, and I do have to say that in some cases I'm quite jealous of people having a strong type checker to aid them, because what happens in Clojure oftentimes is that you just kind of chase around some types of errors that would be very simply prevented by just having a type checker, and here you have to spend time thinking about, okay, what went wrong. And like, if you notice, like, I'm super allergic to having to think about things that aren't the problem at hand. So anything else is just needless distraction, and I don't want it. And here's, unfortunately, Clojure being dynamic fails. Or rather, it did up until recently when we got this lovely library called Clojure.spec, which does allow us to have very powerful descriptions of data. Essentially what you have is sort of a regular expressions for data structures, along with obviously using any arbitrary predicates and so forth. And this is again just a description of this. Again, it's described as data, so you basically have data describing other data, and this allows you to do a lot of kind of very interesting things in how you can query it and so forth, because instead of having maybe types that are visible effectively only to your compiler, you have types that you can interact with as you program. And actually, like, it's incredibly trivial to build, maybe to have a graph database on top of this, and then there are just various queries on that graph as to how your kind of types, or rather data descriptions, how they interact together. And this turns out to be very helpful, especially when kind of working with some new data set or things like that. Just kind of a brief overview of what Spec does, because I think it kind of might have interesting implications to the crowd here. So like, fundamentally, it achieves 4 things with those kind of Clojure descriptions. Now, I won't go too much into it because like, you're not predominantly Clojure crowd and it doesn't really matter. But the idea is that like, you have fundamentally some way to describe your data structures, which uses effectively regular expressions to describe it. And then what you can do with this are 4 things. You can do validation, so just see if like, any chunk of data I may have, does it comply with with my data description, with my spec. The second is it can use those specs to generate tests. Now, those of you who know Haskell, in Haskell you have quick check, which was probably the main influence in doing this test generation. And the idea is that you just take the description and generate tests from it, and do effectively just cover the whole basis. Now, those two together, having validation and doing and having tests built automatically, means that we essentially have a poor man's type checking, because otherwise the problem, sure, you can, like in any dynamic language, you tend to have this some type strictness where types are checked, but they're only checked at runtime. So you might have some class of errors which aren't always manifest, and it kind of becomes messy to find them and things like that, or something like might explode down the line where you're least expecting. Now, with using test generation, this is kind of solved because you just cover most of the bases and can find the majority of errors. So we're kind of halfway there. I'm really excited about the promise of this approach and how it ties to this general notion of working in dynamic languages. And it does bring something to the table which you won't necessarily get with a classical type system, or would be kind of hard to express. Things like, because you're just generating tests do for you is, for instance, they find errors stemming from numerical instability. This is something that if you're working with numbers, it occasionally will, especially if you implement something on your own, it will bite you, and it's kind of pretty hard to guard against if you aren't really thinking about it. While here, it will generate various values, and in my experience, it's very effective at finding this kind of numerical instabilities, and then the whole thing blows up if you have some constraints on what you expect your results to be. And this was a very unexpected but a very nice addition to what Clojure Spec brings to the table. Now, the other things you can do with it is, essentially, it can act just as destructuring or pattern matching. So it's another way that allows you how to reach into the data structures and get bits and pieces out of it based on this kind of regular expression like description of your data, which also turns out to be very useful. And the last things are just using it. You can also define transformations on those bits on the data. And so essentially it acts as a macro system for your data. So like if macros normally in Clojure would do, you take a code, which is again data, and transform it. And here you can do the same thing, just describe it as kind of recursively as how data gets transformed. And if you have a nested structure, you don't need to have some parser that is aware of all the various permutations of how your data can be composed, but I just define it for each individual small piece that knows how to transform itself, and then the whole thing is built from that, and you get a transformation of any arbitrarily complex data structure for essentially free. Okay, so in terms of how, for instance, we use it concretely, and what it gives us is like just a brief overview of what our data layer looks like. It's essentially we're using Kafka as this main message bus, to which we write all the events and all the external data, and then we take those out and build various pre-computed views with it. Now, I'm a big fan of pre-computed views because they allow you to essentially to first of all save some time when you just kind of want the data in the same shape anyway, time after time, and reduces the chance of you making a mistake when you're just assembling your data in the shape you want. And the last thing, which is probably the most important, and oftentimes it extends the time of how long can you do computations on your machine rather than having to have it run somewhere in the cloud. And this is kind of a big thing because for all the lovely frameworks for distributed computation that we have, it's still, let's face it, it's more convenient if I can work on things on my computer alone. And it tends to be faster and with less ceremony. So this is something that's very worthwhile, and if you are smart or diligent in doing your materialized views, your pre-computed views, this is something that can oftentimes greatly extend how big of a data set you can work with on your computer. But the problem here is that if you really want to be diligent about it, it takes a lot of time and a lot of care to think about all the various permutations of views you might want to have. But if we have a nice description of the data coming in, which we now do with Spec, what we can do is then just define some ontology and various inference rules based on those descriptions and just generate views which is completely data-driven by the description of the data coming in. So you can just have various rules of, okay, for instance, if you see that in this data set you have a field called user, then derive a view which enriches this with, for instance, some historical data about how long this user has been a user and so forth, which segment it belongs to and stuff like that. And this can be done completely automatically just based by having a rule that says, okay, if you find this kind of field, do this. And you can also, what we're also doing, for instance, is various statistical analysis to figure out if there is a strong seasonal component to some new data, and if it is, generate views which take this into account, and so on and so forth. And this is like, essentially, something like this is my go-to topology for working with data. So essentially, like the text picked doesn't really matter, but effectively just have a way to ingest all the various events and then store them into various shapes. Have the data in a raw form, so you aren't losing data, and then build off of this like progressively more and more aggregated views of data, which kind of make the main sense that you have. And this kind of turns out to be a very scalable approach, and it doesn't require that much upfront thought or engineering. Okay, so moving forward to a completely different topic, but still in terms of doing, in terms of environment to work with data, it's very important that when working with data to have this notion of how the entire distribution I'm working with works, rather than just looking at some specific numbers. And so it's important to have some means of visualizing this. Now, what the data science community kind of standardized on are various forms of notebooks, be it Jupyter or Zeppelin in Spark and so forth. And here again, we are using the same thing, but also, like, I'm not entirely convinced that notebooks are always the right way to go. Now, in some, like, coming from a Lisp tradition, obviously, my go-to alternative would be a REPL. And so the question becomes, okay, notebooks versus REPLs. Now, the answer is obviously both, because each one has its unique pluses and minuses. The thing that I like with REPL is that it's ephemeral nature. So if I just want to try something out, I can do this, and it doesn't kind of pollute what I'm actually doing, and I don't have to constantly maintain my notebook to remove all the various small bits and pieces when I was trying things out. Because, like, I'm horrible. I don't remember any APIs, how they look like. I constantly make errors, so I experiment with a lot of things in the REPL just to kind of to get it working right. And in Clojure, you also have, of course, various introspection mechanisms, and you can just get documentation on various functions from the REPL and so forth. So you do a lot of things which you don't want to be contained in your end result. And so for those things, REPL is perfect. But on the other hand, what the notebook brings to the table is the ability to have spital grouping, meaning to group together things that can work there and really take someone through your thinking, but somewhat censored for all the small digressions that you've made. So ideally, you would have both. And luckily, you, by the virtue of the whole REPL system in Clojure, you can have both of them, because the way it's done in Clojure, in most Lisps, is that essentially you have, on one hand, a REPL server to which you can then connect many clients. So what we can do is, in fact, have both the notebook and my REPL session, wherever, for instance, in Emacs, in my case, running off of the same REPL server, meaning off of the same running instance, and I can just kind of use both of them. And the second thing with this approach is that a REPL server also has middleware. So I can inject things, or I can define how this communication works and inject things. And the idea is basically that I might want to do some dispatching and then transformations based on the results I get. So I can have a client that's more or less agnostic about this, which just sends some computation to my REPL server, and then the server does the computation and you get some result back. And now, based on some arbitrary predicate about this result, I can then choose and manipulate it further. So for instance, here is a very stupid little example of, let's say you want to be able to print out infinite sequences. And now that obviously won't be a very good idea if you just kind of say print this. So we want to truncate them at some point. And what we do is we just kind of use the protocol that's that dictates how things are rendered on the client side, and define a new kind of way of viewing this, where it just takes the first 10 values and then puts ellipses after it, and you get this new representation. Now, obviously, this is just a toy example, but the point here is that this is something I can type in my notebook, send it to evaluate on the server, and this code will actually influence how the code is evaluated in the server and what's getting sent back to the REPL client. So instead of having this infinite sequence, which would be problematic, to put it mildly, what it does is it already kind of, this will run on the server side and will send already the truncated results back to my notebook. And this is a very powerful idea, that you can have this kind of seamless merger of your runtime environment and of the things you're working on. And this is also and this is the thing I miss about any of the development environments that we can have off the shelf right now, even like Emacs, which tends to be very well regarded in the Lisp community and is the bastion of what a powerful environment looks like, but it still has this problem of having a completely your development environment being a completely separate environment, and you, at the very least, you have to context switch between, okay, now I'm developing for Emacs to get something done, and now I'm actually working on my own program. Rather, I think that the way forward is to just kind of have the melt of both of those things. And then this allows you that notebooks can suddenly become more. They can become live documents. They can become dashboards. They can become one-off tools. You just kind of start with this amorphous notebook and then develop not just solving your problem, but also building small tools specifically to visualize or work with the problem you have at hand. And this is I think for me, is the core essence of a more engineering-centric approach to working with data, that you're constantly building small tools as you go along and work on those data. Now, but still, there is probably the most nagging problem with using Clojure for data science, and this applies to many of the most interesting languages out there, is just the ecosystem. The more you want to do something domain-specific, like working like data science or whatever, the more you run this problem of there are probably not going to be all that many libraries. But this is actually kind of a non-problem in a lot of ways, because what you can always do is you can just farm it out to, for instance, for machine learning, you can use scikit-learn. For visualization, you can use ggplot and so forth. And the idea is that you just kind of write mini compilers where a DSL which generates appropriate code, for instance, in Python, sends it to Python to be executed and gets the results back. Now, this might seem awfully crude, and in other ways it is, but it also works surprisingly well. And when looking at what actually, if, for instance, in terms of machine learning, the runtime is obviously going to be dominated by just the algorithm running. So it doesn't matter that you incur some overhead when shuffling data back and forth. And this allows you in literally like 10 lines of code to get anything from a huge ecosystems like the scientific community for Python and have it running Clojure and use Clojure for where it's good, meaning just getting the data into a shape you want to work with. And the same thing, for instance, like in the library I was talking about, one part of it called huri.plot is exactly that. It's a DSL that compiles to ggplot. That's one of probably the best visualization libraries out there, running on R, and it completely follows the rest of the design philosophy behind this library. So it's kind of composable, blah, blah, blah. But it's still underneath the hood. What it does is just generates R, send it to an R instance, and then gets the SVG back. So you can basically, with very little code, you get all those nice plots that would take ages to develop in Clojure otherwise. And here just just a couple of hundred lines of code to account for the various ways things can kind of get together and options and stuff like that. But it's super trivial code, basically just programming against the API of ggplot. And instantly my Clojure world becomes that much richer, and I can have nice visualizations. Right, so in conclusion, basically, there are four main, I think, takeouts from, or rather, the four main things I would like you to take from this talk is. The first one is just when, and this is probably the most general one, when doing data science, especially like the more exploratory kind, speed of answer actually matters. It qualitatively changes the dynamics of using data in your company, and this has very widespread ramifications. The second one is that we don't have to reinvent all the wheels in our language of choice. So feel free to use obscure languages and just then mine all the other ecosystems for anything that's useful. It turns out that this kind of language interoperability usually is not that big of a deal as long as you don't have super long start times or something like that. But if that's not the issue, then this is a way to very easily extend your ecosystem in a very natural way. Now getting to the more philosophical points, I think that working data science is fundamentally about various encodings and representing information rather than some specific mathematical notions like matrices or distributions, or that's kind of, those are all, again, just a different kind of way of encoding information and communicating this information, but it's not necessarily the only or the best way. And when arriving at that, it oftentimes makes more sense to stay more in the world of just various structures and encoding computation and encoding meaning in structures rather than being tied to just the mathematical notions which were designed with completely different objectives in mind. And oftentimes, like even if you look at just the mathematical notation, it optimizes for just the ease of writing it in a way and being able to communicate very complex ideas on paper, while we're using a dynamic system. Oh shit, sorry. A dynamic system that can respond, and actually we can be in a dialogue with it, and that drastically changes the affordances of what an ideal notation would be. So keep this in mind. And the last, and I'm hoping the biggest takeout, because this is something I would love that more work would be done on, is this notion of blurring the line between your environment, the environment where you're working in, and what you're actually working on, and having just like one continuous session and one continuous environment. And again, this is a very old idea. If you look at the old Lisp or Smalltalk systems, this is exactly what they did, but then at some point, we kind of diverged away from it. And I think we need to return to that and start to approach solving problems more in terms of building very small tools which solve just one specific problem, and not actually just kind of coding against our environment or within the limitations of either our environment or language, but rather shaping both our language and our environment to solve our problems. Now, the Lisp tradition is, and something that's still alive, is big on building small languages to fit to a problem, but I think the next step that we all need to embrace is also building kind of small environments and small tools to help us solve our problems. And with that, I turn to you, and if you have any questions.